Hi students, welcome to my lectures. I hope you are following my lectures from the beginning. We are in the chapter of finding the volume of a gas or a liquid at a given pressure and temperature conditions. Now we have covered the liquids, and in the gases, estimation of volumes, we have covered ideal gas as well as virial equation. Now we are into the one of the important concepts of estimation of volumes using cubic equations of states like Van der Waal, Redlich-Kwong, Soya-Redlich-Kwong, Peng-Robinson, these kind of equations, and there are many other cubic equations of state where we can use these kind of equations to estimate the vapor, the volume, molar volume of the vapors as well as the molar volume of the liquids. You can see here also I have mentioned the equation of state, cubic equation of state for estimating the liquid volumes. Here also cubic equation of state for estimating the vapor volumes. That means the cubic equations of states are designed in such a way we can estimate, we can most probably, we can use it for the liquids as well as the vapors. So let us go ahead and let us see what exactly the cubic equations of state are. And here it itself giving the information, it is cubic. That means the equations which represented, these are called the equations are in cube root, right? That is the cubic equations of state. That means whenever you try to solve the equations which are in cubic in form, you are going to get three different roots. That means the cubic equations will equations of state will give information about the three different volumes. Because it's a cubic in nature, the roots of the equation will get three different volumes for a given pressure and temperature conditions. Now it is our duty, right, whether the volume we have estimated using the cubic equations of state are for the liquids or for the vapors, among the three roots, which one is most appropriate and which one is correct and which one is wrong. Because sometimes the volume, when you try to solve these equations, you might get there are three equal roots, or there are some roots where two are same, one is different. There are some their imaginary roots will come. So it is our job to identify whichever may be the values we get from the roots of the cubic equation, whether we are it for the liquids or the vapors. Let us move into the concept of cubic equations of state. So if you remember the PV curve which we are trying to follow from the beginning of this lectures, so by observing this PV graph, you can see on left hand side of this blue curve it's a liquids, on the right hand side of the red curve it is called vapor or a gas, and in between these it's called liquid plus vapor mixture. So the cubic equations means this line is nothing but the equation of state. So the line passes through all the liquids, even liquid plus vapors as well as the vapor side. That means this line, which is an equation of state, which can able to used to find the volume for a given pressure and temperature informations. As you can see, if you conduct experiments with any particular substance at different pressure and temperature conditions, you get some volume informations. Okay, so that is what the cubic equation of state. So it can able to identify liquids as well as the gases, but you can see the line, this cubic equation is also passing through the vapor plus liquid mixtures. Generally, cubic equations are not accurate for the liquid plus vapor. That means if a container consisting of liquid and plus vapor both, then cubic equations cannot be estimated, cannot be used to estimate the vapor and the liquid volumes. It is quite appropriate if this cubic equations of state is on the liquid side, then you can get the liquid roots. If this same cubic equation of state, if it is on the vapor side, you can estimate the vapor volume. That means liquid volumes as well as the vapor volumes can be estimated using this equation of state. But you get some information about the mixed state also, because the line is passing through the vapor plus liquid mixture also. So in such cases it will give certain volumes which are in between the liquid and the vapor. You should ignore, because these are unstable states. So sometimes you don't need, as per the cubic equations of states, equation of state is concerned, only you can able to judge whether you have calculated the volume is for the liquids or for the gases. So Now we are trying to follow this particular curve. This every curve is one cubic equation of state. That is estimation for the cubic equations of state. This every line is at a constant temperature. Example, this is at a this line is representing you are finding the PV graph at a constant temperature line. So this is at different temperature, this is at different temperature, this is at different temperature, this is at different temperature. That means as you increase the temperature, the line, the shape of the line and the shifting of the line going to takes place. Okay, every line is one cubic equation of state, which could be Van der Waals, which could be Redlich-Kwong, which could be Sawyer-Redlich-Kwong, which could be Peng-Robinson. Okay, then why it is necessary? See, as most of the things we are going with the ideal gas, because you can able to find out the vapor volumes if you imagine it is an ideal gas inside the chamber, and ideal gas assumes that there is between the molecules there are no attraction forces, okay, intermolecular forces, and the volume, if you can volume of each molecule, that means volume of the molecules inside the chamber are less volume compared to total volume of the chamber. That means every molecule in an ideal gas, assume that it has a negligible volume compared to the total volume of the container. So these are then some assumptions. Based on the assumption, the ideal gas equation has been formed. To relax this ideal states, because in reality we have the real gases or non-ideal gases, and we have to estimate the properties of volume at a given pressures and temperatures using the other equations, like as I told you that virial equation that we have discussed here, one of the cubic equations, right? Now we are in the part of cubic equations. It is also used for estimating the non-ideal gas states. Okay, let us see happen how cubic equations. I told you that it is going to give 3 volumes. Let's say a big cubic, it will give 3 roots, that means 3 volumes. Out of these 3 volumes, which one is appropriate, which one is on the liquid side, which one is on the gas side? That is what we are supposed to find out. Here is one such an example. If you see, it's a Van der Waals equation of state. That means the first equation of state, which we are going to discuss at the later stages. The equation of state looks in this way. P equal to RT by V minus B minus A by V square. Okay, these are the certain this is how the Van der Waals came up with this kind of equations. A, B, normally it accounts for the non-ideality of the gases. Okay, some B is something accounting for the volume of the molecule, some A is accounting some intermolecular forces between the molecules. So all the non-ideality he is encrypted in the terms A and B here. So for different molecules, the value of A and B are different. So if you know A and B, so you can able to estimate the volume of the gas from a given pressure and temperature informations. This is how we got. I hope you understood that equation of the line. Let us move ahead. So let us take example. Let us assume that you are in a vapor phase. How we can say, example, there is certain amount of substance present at certain pressure and temperature. You are supposed to find out the molar volume of this particular molecules. That means first of all you need to identify whether you are here the substance present in the chamber is a liquid or a vapor. Okay, I already discussed that how we can able to find out, because if you refer to my earlier lectures in the present lecture series, that I have gone with some simplest form identification of a phase. If you refer to that particular lecture, that means based on this saturated conditions, temperatures and pressures, you can able to judge whether whether the substance is in the vapor phase or a liquid phase. So if you kind of get to know that information, then you can able to whatever the equation of state, okay, the value, the vapor volume which you are going to at this pressure, at this line temperature, that means at certain temperature, at this pressure, what is the volume? This is the volume, that is molar volume of this particular gas is this particular value, which is you can be estimated using using the graph or using the equations. So what is this cubic equations of state? Imagine this is also one cubic equation of state. Okay, that cubic, one such a Van der Waals cubic equations of state, this you can see the volume is at the denominator, square terms are there. So this is somehow, it's a cubic equation. That means if you try to solve this particular equation, you are going to get 3 different volumes informations. Okay, and how this is that means what are the roots of this particular equation? Assume at this particular, that means I am trying to calculate the volume at certain pressure and temperature. So pressure is fixed, that means you have to drop a horizontal line which is at this particular pressure. You wanted to find out the volume. So this particular line is a temperature line. That means this is particular line is a constant temperature line. That means at this particular temperature, at this particular pressure, what will be the molar volume of the of this particular substance, which is in the vapor phase. That means it is in the vapor side. Or if you don't have this particular graph, you have to identify the phase, right? Using identification of phase, my lecture you can follow. Now let us assume that presently it is in the, this line is on the vapor side. That means whatever the volume I am going to calculate using this particular equation should be the vapor volume, because the substance is in the vapor phase according to the particular graph. So if what is this talks about, P equal to, example, P equal to 30 bar. So this is a 30, draw a horizontal line, and this equation is nothing but van der Waals equation of state. So both are going to meet at one point. That is called the roots of an equation. That means at this particular pressure, that means this is one line which I am interested. That means at pressure equal to 30, I am interested to calculate the volume. That means consider this as a one line. The second line is van der Waals equation of state. Both are going to meet at one point, which is a common solution for this particular horizontal line and this particular equations of state. Okay, that means the solution is the molar volume of the vapor according this particular equation, and this particular equation pressure equal to 30 is vapor volume. That means you somehow if you try to solve this particular equation at pressure equal to 30, you are going to get 3 volumes. The 3 volumes could be the same point, or 3 volumes could be one on the left hand side, some are the imaginary. Don't worry about that. One should be real. Okay, that means it exists as a real substance. That means whatever the volume you try to calculate, it should be the real volume. It should not be the imaginary volume. Second thing is it is on the vapor side. That means whatever the volume it is going to estimate it through this equation, definitely it should be the vapor volume, because it is on the vapor side. So van der Waals equation, roots of an equation might be at least one real root, which is the volume of the vapor. Imagine a dome. This is an experiment. Imagine that this is an experimental dome you have. So for simplicity, so any line outside this particular along on the red right side to red line is a vapor, left side to blue line is a liquid. Okay, this is what the cubic equations of state. Okay, let us try to get one more information, that now this line is on close to this particular point. That means at this particular point, this is called critical point. Okay, at t equal to tc, then how it looks like. So here I am also interested in, because this is my van der Waals equation of state or cubic equations of state, you can assume that this is I am interested in at this particular pressure, at the critical pressure temperature t equal to tc, I have to find out what is the volume. It is very simple. I mean, draw a horizontal line, and this line using this particular equation, wherever these both are going to meet, that is the common point for, that means the roots of the equation. That means whatever the volume which you are going to get through this equation is nothing but the critical volume. Okay, this is how you are going to judge. If you don't have the graph information, it is very simple. Solve this equation at pressure equal to 25 bar. So you get a 3 roots. 3 root could be same roots. All 3 could be same real root. Okay, don't worry about it. While you're trying to calculate the things, it will be more easy. It's very simple. Now whatever the volume information you are trying to calculate at the pressure equal to 25 using this and using this particular equation of state cubic, then you get certain volume. Okay. Let us take one more example, and now this line is in this particular dome. Now see, the things are let us say now this particular line, it's a cubic equation of one is t less than tc. Earlier example is t equal to tc line, before that t greater than tc line, now it is t less than tc. That means whatever the temperatures that means have kept in this chamber, it could be less than this critical temperature. So you can see this particular example van der Waals equation of state has gone through this particular route. Okay, if you plot a P versus V using this particular equation, using this particular equation, if you try to plot a line, the line goes this way. Okay, because it is less than critical temperature, the line takes different turns and twists. For example, you know that example at pressure equal to 20 you are interested to find out the volume. See, the horizontal line is meeting this cubic equations of state at only one location. Okay, then you get some volume information. Then which volume it is, whether it's liquid volume or vapor volume, liquid or vapor, which one is the right? As you know, this left hand side to the blue curve, it is a liquid. So whatever the volume you are going to calculate, it is going to be the liquid state. That means the volume you have just estimated through this particular equation is nothing but the molar volume of the liquid. Okay, that is what the beauty. So it is not touching, because this particular line is touching only at this only one particular point. Okay, imagine you have dropped the pressure to 15, from 20 to 15, then estimated what is the volumes, and you can see the horizontal line is meeting this particular cubic equations of state at 3 different locations. So that means if you try to use this equation and estimate and measure the volumes, it is going to give the 3 different volumes. Okay, then which one is, that means if it is trying to give 3 different volumes which are just inside this particular dome, that means it is touching the dome, that means the one extreme root will be of the saturated liquid, one extreme root will be of the saturated vapor, the middle one is the liquid plus vapor. Okay, but using this, as I told you, that equations of cubic equations of state will not, because it's unstable root kind of. Only thing is, if you're trying to find out if you got the 3 roots by solving this particular equation at the pressure equal to 15, then on the lowest volume will be the volume of the liquid, the highest volume will be the volume of the vapor. Okay, this is how sometime you if you less than the critical temperatures, I mean, these situations may come. Okay, then, and which one is correct? Okay, we got the 3 volumes. I told you the center one is an imaginary, I mean, kind of unstable thing. Then the one which will be on left side is the liquid and right side will be vapor, and simultaneously 2 volumes are given. That means at same temperature, example T, at certain temperature T, at pressure equal to 15, there is a liquid as well as there is a vapor. How that is possible at the same time in the container? It's very simple. Water at 1 atmosphere exists as a liquid at 100 and vapor at 100. That means at 100 degrees centigrade, water can exist as a liquid, that it is called a saturated liquid, and what if you add up a small amount of heat, it turns to the vapor at same temperature. So these are called saturated conditions. That means the volume which you get, 2 volumes, for example, that means liquid water volume and vapor water volume at same 100 degrees centigrade only. This is what the saturated conditions. That means the moment you are going to get 2 extreme roots, that means that you are at a saturated state. That means liquid can that this particular substance can be at a liquid state, or this particular substance can be of a vapor state, depending upon how much energy. If it is having lower energy, it will exist as a liquid at 100. If it is having a higher energy, it exists as a vapor at 100 degrees centigrade. Okay, so this is how you have to tackle if you are in this particular domain. So let us say you have reduced even less in the container. That means I wanted to find out the vapor volume or a liquid volume at a pressure equal to 5 at temperature T less than Tc. Imagine if you drop a straight line at pressure equal to 5 bar, it is meeting this particular line only at one location. Okay, that whatever the volume you have got by solving this equation of state at the pressure equal to 5 should be the vapor, because it is outside this vapor. I mean right side to the red line. That means on this side of the graph it should be the vapor. That means at this condition, whatever the volume we are trying to calculate, it should probably be the vapor volume. So this is how you have to judge, okay, whether you are greater than the critical temperature or equal to critical temperature or less than the critical temperatures. So I hope let us move. This is what the main task. So I hope you understood the concept of cubic equations of state and finding out the vapor volumes and liquid volumes and identification of phases. Let us move on to the next lecture. To solve, let us using take one example van der Waals equation of state or so. We are going to solve one example, so things will be more clear. Thank you.